almost forgot that. Okay, so welcome to the review session. So from the review session with Michelle and Jahan, this is just a basic review. So the overall amino acid structure, you have your amino group, the main things you have are the amino group, the side chain, R group. The R group is what is variable between all of the amino acids, and you have your carboxyl group. Real quick, does anyone want to say what bonds hold these amino acids together? Either unmute yourself or in the chat real quick.
Polypeptides.
You say polypeptides?
Yeah.
That's what is formed when the amino acids bond, but a peptide bond is what holds the bonds together. Also, let me know if you can't read my writing because it's not neat. So, and is a peptide bond a covalent bond or a non-covalent bond?
Covalent?
Yep. Peptide bond is one of the few covalent bonds that we're going to talk about. So it's super strong and it holds together the primary structure, which we'll talk about in a second. So when two amino acids form together, what is the byproduct of that reaction? Yep, water. So the OH of the carboxyl group combines with an H from the amino group, and they form water and a peptide bond. So, what? Thank you. So does anybody have any questions about that?
No.
Awesome. So moving on. A lot of people have been having questions about domains and subunits, so we want to go over that real quick too. So the big thing about a domain is that it is part of so it's part of a single protein, right? And it's a section of the protein that folds independently of the rest of the protein, and it carries out a specific function. So we'll talk about proteins that are responsible for like opening a channel or something, and the other part of one domain on the protein will be responsible for opening a channel, and a separate domain on a protein may be responsible for a different function, right? And so the domain is a section of the protein that folds independently from the rest of the protein, and it carries out a specific function. So another thing that Laura mentioned is that domains are evolutionarily conserved. So you might see a question like, for example, that what part of a protein or two different proteins are the same across like different species or something, and that would be like a domain because they're evolutionarily conserved between species. So a subunit it's part of the quaternary structure. So if you have multiple polypeptides combined together, that would form a quaternary structure, and a subunit is just like one of those polypeptides. So for example, this red one or this blue one would be a single subunit of the whole protein. So a subunit is just one polypeptide in a protein with multiple polypeptides. Does anyone have any questions about that?
Well, the other day it was right here, and Dad put like a plate of food over it. I didn't even know what it was. Yeah, literally, it was. I put it right here. I didn't think it. You literally.
Okay, we're gonna move on. Yeah. Okay. So, is it showing the next? Can you guys see the practice question, or is it still showing the domain subunit slide?
Still showing the domain and subunit.
Hmm, that's weird. Okay. I don't know why it's doing that. 1 second. All right, there we go. Okay, so practice question. This is something that you might see on a quiz or an exam or something. So, like I was saying before, two different proteins have the same domain in their structure. Which of the following is true? Does anyone either put it in the chat real quick or unmute your mic? Yep, so a bunch of people are saying B, so yep, that is the answer. So domain, like I was saying, domains are evolutionarily conserved, so at least some part of the proteins will have a similar structure. Then because they're evolutionarily conserved. Yeah, so going along with that, true or false, a protein with one polypeptide can have multiple domains. So a bunch of people are saying true. I did see one false though. So a protein with polypeptide can have multiple domains. So like a protein can have as many domains as as is feasible. So like I was talking about before, a protein could have one domain that has one specific function and another domain that can have a separate function. So a protein can have multiple domains. It doesn't have to, they can be on the same polypeptide too. It doesn't have to be different polypeptides. They can, a protein with one polypeptide can have multiple domains. I don't know how to explain it anywhere else. So does anybody have any questions about that? Okay, I'm going to move on. So now Sebastian's going to talk about this.
Okay. All right, y'all. If at some point you can't hear me, just let me know in the chat or interrupt me. That's totally fine. So I'm going to talk a little bit about polar and non-polar stuff. Refreshing your knowledge on this is going to be super helpful because a lot of the bonds that we'll talk about later refer to whether something is charged or uncharged. So if you want to refresh on polar, non-polar, feel free to ask with any questions. How do you guys feel as of now with polar versus non-polar? You could give me like a check or thumbs up, or I don't know what the features are in this one, but or drop in the chat how you're feeling. Good, not good. A little review, sure. Okay, so something that's polar is like this water molecule, for instance. I'm sure you've heard like dipole before. Dipole literally just means two poles. So di means two, pole means like two sides. So this water molecule has two sides. The oxygen is very electron rich, which makes it partially negative, and the protons down here are very electron deficient, which makes them positive. So the water is a perfect example of a dipole, where CCl4, if you notice, the electron distribution is going around pretty much everywhere, all across this molecule. There's no two sides to this molecule. So CCl4 is not a polar molecule. And again, that's going to be relevant when we talk about different proteins and how they interact with each other. Are they interacting as a dipole-dipole, as an ion dipole? How do you guys feel about that kind of terminology? Also, by the way, like ion dipole, dipole-dipole, is that okay? Okay, so I'll move on from this one for a little. And again, if you need like any help with something, you could totally drop it in the chat or just interrupt me. Okay, so you've definitely seen this chart before. These are pretty much all of the amino acids separated into the 4 different categories. So everything here are polar amino acids. Some are charged and uncharged, but nonetheless, these are all polar. Polar molecules are always hydrophilic, which means that they're going to be attracted to water, and the non-polar ones, just the ones on this side, those are always hydrophobic, so they repel water. A key thing to remember is that proteins will typically fold when they start folding into their tertiary structure. They're going to conceal the non-polar parts. So if there's a polypeptide with some R groups in this category, in the non-polar side, they're going to tuck those towards the inside. Because again, if you're in an aqueous solution, if you're in water, the parts that are hydrophobic, the parts that repel water, obviously are going to go into the inside. Or the hydrophilic ones, the polar charged or polar uncharged, will be exposed to the aqueous environment. Okay, do you guys have any questions about that so far? Okay, so I have a question here for you. In a peptide chain of 10 amino acids, what will happen to the protein in terms of the protein folding if you change the 5th amino acid from a valine to a glutamine? Yeah, these are very common quiz questions or practice assignment questions, as you probably noticed. Laura loves these kinds of questions, so definitely practice these a little bit. So if you go from valine, which is, where's valine? Right here. If you go from valine to glutamine, what do you think is going to happen in terms of the protein folding? Do you think it's going to stay the same? Do you think it's going to unfold? What do you guys think?
That's it. Erase that.
It would definitely change. As for the folding, I think usually the hydrophobic fold more inward to like aggregate together. So if it changed to glutamine, would it then kind of fold outwards to interact with other polar molecules?
Yeah, exactly. If you go from a non-polar amino acid to something that is very polar, like the glutamine, now it's going, well, yeah, it's going to unfold itself. It's going to change its structure. It's going to unfold so that the polar amino acid, like you said, is now exposed to the polar environment. So you will almost definitely see some kind of like dramatic change, right? Well, with reservation about like almost always see, you could expect a pretty dramatic change if you go from something very non-polar to something very polar. Okay, so how about if something is going from glutamine to cysteine? This one is, you have to think a little intuitively about this one. So from glutamine right here to cysteine.
Wouldn't it fold inward so that way it can conceal its non-polar group?
Yeah. Sorry, we're just admitting people in. Yeah, it would definitely start to fold more inside because you're going from a polar amino acid to a more non-polar. It's going to change its shape again, and it's going to try to conceal itself a little more. However, if you notice about cysteine, I don't think I could, but that's okay. If you notice, the thing about cysteine is that you have a sulfur group right here. So sulfur isn't a very electronegative atom. It doesn't draw electrons as well as oxygen or nitrogen. But because of the fact that it does have a pretty good electron density around it, meaning that sulfur has a good amount of electrons hanging out around it, it is slightly, it's not polar enough for it to be in this category, but it is slightly more polar than if you had alanine or valine or something, right? So you would expect to see it turning inward to conceal the nonpolar side, but maybe not as dramatically as if you went from valine to glutamine. If you go from valine to glutamine, you can expect a pretty dramatic shift in the protein unfolding. But if you go from glutamine to cysteine, it technically will shift again. You can expect to see some shifting, but maybe not as much as you would see if you went from valine to glutamine. Does that make sense?
Yeah. And am I right to assume that I would see a question like this on an exam to trip me up?
It's honestly very possible. I don't know if like, you know, like I'm sure the intention isn't to like trick you guys, like to get you or anything. But the questions will definitely prompt you to think intuitively about these things. So that's an answer that personally I would put on an exam. If something is going from glutamine to cysteine, I would expect to see some unfolding or whatever. but maybe not as bad as if it went from something very, very non-polar to something polar.
Mhm.
Does that make sense?
Yeah.
Cool.
Laura's exams are all about problem solving, so she's gonna ask you to like change. She'll see questions like this all the time. Where you ask you like change something about the structure of a protein, and then what affects its what is the like functional effect of it.
Yeah, definitely. So if you want, like, you could practice like, okay, what if it's going from lysine to arginine, or what if it's going from phenylalanine to histine, whatever. So you could just practice that on your own.
Yeah.
Okay, you're taking this one, right?
Yeah. Okay. All right. Well, real quick, did anyone have any questions about what we just went over? This chart, she posted everywhere, but this is probably like one of the most useful charts for like the first exam.
Yeah,
So
if you could keep a copy.
you should probably like print it out or something if you can. Just have it next to you. I have a question. Someone said I have a question about ionic bond. When does it occur? Do you want to take that?
Sure. Okay, so an ionic bond is technically when two charged. Okay, so really get to know the difference between polar charged, polar uncharged. Do you mind if I draw it? So these are all polar, right? These are all polar amino acids, but only these are polar charged. So you would see an ionic bond only with polar charged species. So if I put my lysine with the aspartic acid, that would be, or the result would be an example of an ionic bond. But if you were going from something like lysine to glutamine, even though they're both polar,
I was asking her all the questions about the left shoulder. She's
No,
like,
when I
yeah.
went there, I said it's your shoulder. They said it's your
Or her right shoulder. I was asking her all the questions about the right shoulder. Now I'm getting.
all right, guys, if you could, if you don't mind like keeping the mic mute, unless like you have a question, of course, please do that. But anyway, did I answer your question about ionic bonds? Okay, sweet, no problem.
Awesome. So I'm going to move on. I'm going to talk about the chemistry of primary and secondary structures. So primary structure, as we've been going over, is just the sequence of amino acids held together by covalent bonds or peptide bonds. So like we were saying, the OH of the carboxylic acid and the H of the amino group, they bond together and they form a peptide bond between them, and water is the byproduct with the result, like the extra atoms. That's called a dehydration reaction. She'll never ask you like what kind of reaction most likely, but if she does, it's a dehydration reaction. So yeah, make sure you know that the bond between two amino acids is a peptide bond and it's covalent. And because it's covalent, it's a super strong bond, so it's hard to break by most denaturing things. So for secondary structure is alpha helices and beta sheets. And what forms alpha helices and beta sheets are hydrogen bonds between the backbone atoms. So secondary structure does not involve R groups. That's pretty key. You'll see questions that like ask you some stuff about that. So this should be like, which of these interactions, like, would be an example question she'd ask for like that?
It'd be like in secondary structure, what groups are involved in hydrogen bonding, and you would see like only the amino group, only amino and carboxylic, or R groups and carboxylic.
Yeah,
things to that effect.
Something like that. So make sure you know that secondary structure is only involving the backbone atoms, so amino groups and the carboxyl groups. So practice question to build on that. In alpha helix, the R groups of the amino acids in the alpha helix are available to make interactions with other parts of the protein and or with other molecules. True or false? Just unmute or type it in the chat. Seeing one false, one true, a couple trues. All right, this is good. We have a solid mix of.
I wish we had the poll function.
Yeah, no, it'd be good to have poll function, but we're seeing a solid mix between true and false, which is good. So now we can explain that. So in an alpha helix, the R groups of the amino acids in the alpha helix are available to make interactions with other parts of the protein. So like we were just saying, the alpha helix is a secondary structure, so it is it does not involve the R groups. So that means the R groups are still available to make interactions with other parts of the protein or with other molecules or other proteins. Does that make sense? So like Laura was saying, the R groups will go like this, so they'll stick out. They'll be alternating, and then so like but like an alpha helix will not involve those R groups at all. This isn't even relevant for that, but yeah. But so like, why is that the case? I guess I just explained that. My bad. Yeah, so they are available because they're alternating inside and outside of the helix. Yeah. Or wait, not alternate. Wait. What's the difference between B and C?
Well, actually, for A.
Wait, not inside and outside the core helix. No, so they're sticking away. Does the core helix just mean like the non?
Yeah, the core of the helix refers to the center of the helix, the inside. Your R groups of the helix are going to be sticking out of the core. Doesn't the R groups face away from each other? Yes. I think the alternating may be for beta sheets. Yeah, I'm not sure what.
I know the answer is B, and this is something that has shown up in the past.
Are you trying beta sheets?
No, I don't. No, I'm not drawing beta sheets. Where is she? I have to find what that the diagram that she used. So I guess what I'm trying to say is that my notes says alternatives for beta sheets outside. Sorry, let's just go over this again. So the first one was true because the R groups of the amino acids are available to make interactions with other parts of the protein because they're not involved, like we said in the previous slide, the R groups are not involved in secondary structure, right? But I don't know how to explain that there's just sticking out away from the core helix.
Sure, if I could add on this a little bit.
Yeah.
Okay, so for the first part, is true when we talk about tertiary or quaternary structures. So something important to note is that R groups do not play a role in making alpha helices or beta sheets in secondary structure. So when we're solely talking about secondary structure, R groups are not involved at all. That's not in the conversation. But when we talk about tertiary and quaternary, then the R groups of the alpha helices and the beta sheets that have already been formed, then those R groups do start playing a role in making interactions with other parts of the protein, either the backbone or other R groups. So that's why this is true. Oops. So why that is, like why these R groups are available to make these interactions with other R groups or the backbone in tertiary. Let's be clear on like the differentiation on that. The reason why they're available is because they're sticking out of the helix. So if this is my alpha helix, if that's my alpha helix, your R groups are going to be like coming out this way, right? Like they're going to be sticking away from the core. You would never see them sticking inside the core. That's too much steric strain, and that would just create problems.
Right.
Does that make sense?
That's
I have a question.
Yeah.
So, I know usually they would stick out, but so would there be any case where there's like hydrophobic R groups and they kind of like maybe not stick out but like stay closer, or is it like alpha helices typically don't have any hydrophobic R groups?
Alpha helices could have hydrophobic R groups, but when it comes time to, so when the polypeptide is making the secondary structure, all of the R groups are going to be sticking out, whether it's hydrophobic, hydrophilic, whatever. They're all going to stick out. But when it comes time to make the tertiary structure, when it comes time to make the huge protein folding, like when the whole thing starts folding on itself, then it's the hydrophobic R groups. They're going to be tucked away inside.
Okay, thank you.
Sure, no problem. Okay, someone asked what steric strain. Do you want to take that one?
Yeah, so steric strain is the strain that is caused by like molecules that are too close to each other, right? So if we go back to, it's not showing again.
You guys can't see us changing slides, right?
No.
Okay, we're gonna unshare and then share again real quickly. Sorry about
Sorry.
that.
Yeah. I'm sorry.
So go to like move their heads. Structure.
I love technology. Okay. Now it's just, okay. So if we look at these molecules, for example, so if you had an R group for like tryptophan, for example, notice how, or phenylalanine, notice how these amino acids have these big benzene rings. A benzene ring is just this thing. That's just what it's called. So no, those are really big molecules compared to something like just like a carbon with 3 hydrogens. That is much bigger than a carbon and 3 hydrogens. So those would cause more steric strain, because if you imagine like molecules just in space, like just like around together, like molecule with benzene would like takes up much more space than molecule with just CH3, right? And then so the steric strain is caused by that the molecules don't want to be too close to each other and they want to repel. Can you explain that a little better?
Yeah. So steric strain is when molecules are coming into contact with each other. If you have big clumpy molecules, like what Jason was talking about the benzene ring and the tryptophan. So notice this R group in tryptophan, that's a pretty bulky molecule. So if this guy tries to come into contact with another tryptophan, there's going to be a whole lot of steric strain because this is a really, really big group. But if you're working with something like glycine, right, which is just that, or it's like valine. Valine's not as bulky as the giant benzene rings, so it won't exhibit as much steric strain. Does that make sense?
Yeah.
Okay. Okay.
Yeah.
If at any point, yeah, sorry, go ahead.
And then so the reason that's relevant is, so going back to like the alpha helix, so they stick out away from the core helix, because if they were all sticking towards the inside of the core helix, then like that would cause a lot of steric strain because they're like bumping into each other, right? And imagine if there was like a big benzene ring like tryptophan in there, that would cause a lot of problems. So that's why they stick out, so they don't bump into each other. Any other questions on that?
No.
Can you talk about the hydrogen bond and backbone? Why is there one bond every 4 amino acids for alpha helix? What do you mean the hydrogen bond in the backbone? So like,
yeah, they mean like why, or correct me if I'm wrong, or stop me if I'm wrong, but your question is asking could you talk about the hydrogen bonds in the backbone? Why is there one every 4 amino acids for the
Okay.
alpha helix? So the reason that alpha helices need a hydrogen bond every 4th amino acid is just to give the structure more space. It's like the ideal amount of amino acid spacing for you to create a structure like this. So if like you have a hydrogen bond every other amino acid, that's not gonna result in an alpha helix because it's like the hydrogen bonds are too close together. So the H bonds need to be spaced out a little more so that you could create a helix-like structure.
Yeah. In contrast, the beta sheets have hydrogen bonds like right next to each other,
Right.
and that's what creates the sheets. So the every 4th amino acid helps create like the spiral structure of the helix, while like the closer together hydrogen bonds creates the sheets of the beta sheets.
So we need to know specifically which atoms form the hydrogen bonds. The hydrogen of nitrogen bonding with oxygen, other amino acids in the hydrogen central attraction. Yeah, to answer your question about knowing which atoms form hydrogen bonds, yes, you do need to know that hydrogen bonds only form between obviously hydrogen and oxygen, nitrogen, or fluorine. We won't talk too much about fluorine in this class. There shouldn't be like any fluorine in your body, but certainly oxygen and nitrogen will form hydrogen bonds. Is there any way I could clarify your question or like yeah, or did I answer your question, or do you want me to expand on something else that maybe I'm missing?
Hello?
Okay. Did somebody ask a question? Or are we good? Okay. I see a thumbs up.
Okay.
Oh,
Do you have another question?
yeah. Can you scroll back up to like the chart of amino acids? Yeah,
Yep.
that one. How would like a hydrogen bond form between like a polar molecule with a polar molecule? Like which atoms would be working? Like if I wanted to bind like a threonine with like an asparagine, I don't know which one of the H's would move over to the NH.
Yeah. So if you wanted to, yeah, go ahead. If you wanted to, can you see this zoomed in?
Yeah.
If you wanted to see or wanted to know which ones will form hydrogen bonds, just remember that hydrogen bonds always form with either fluorine, oxygen, or nitrogen on. So for instance, if you see that this group has an oxygen, which it does, and this group has a nitrogen, which it does, as well as like a bonding hydrogen here or a bonding hydrogen here, those will form hydrogen bonds with each other. Because you have a bonding hydrogen, you have an oxygen, and you have a nitrogen. Does that make sense? So
So
yes.
which one is giving the hydrogen?
It honestly doesn't really matter which one donates the hydrogen. It could be either one of them.
So on a test, I won't have to say which one is giving which?
Yeah, like I don't think you'll ever come across a question that'll be like which amino acid is donating the hydrogen. Yeah, I don't think you'll see that. You will see something like if you combine serine with asparagine, what kind of interaction will you see? And then you will have to know that it'll be a hydrogen bond, but you know that you have an oxygen here with a hydrogen and you have a nitrogen here also with a hydrogen. So you'll know that they could potentially form hydrogen bonds.
And then you said earlier that ionic bonds only form with polar charged bonds. So
Yes.
what forms in between polar, the blue polar ones and then the purple negatively charged ones?
Good question. So all of these technically are dipoles. So everything here are dipole molecules. So again, a dipole is just a molecule that has two electrically different sides, where one side is more positive and another side is more negative. So if you try combining a positively charged amino acid like this lysine,
Mm-hmm.
with this ion, right? That's an ion because it's charged, with a polar molecule that's not charged, the result is going to be it's an ion dipole because, sorry, let me finish. Dipole.
Okay.
Because you're working with an ion, this lysine,
Mm-hmm.
as well as a dipole, this glutamine. And that's important because you probably will see a question, something like that, or you'll see a question where a lysine is being combined with tyrosine or whatever, and it will ask you what is the most likely bond that will form, and the answer for that will be an ion dipole.
So if I wanted to bind asparic acid to like asparagine, what would form?
You
Would
tell
it just
me, what do
be
you
an
think?
ionic bond, or it wouldn't happen?
Okay, so anything with a charge is an ion, right?
Mm-hmm.
Asparagine is a polar amino acid, but it has no charge. So it's technically not an ion, but it is a dipole. So if you tried combining, like you said, if you tried combining the aspartic acid with the asparagine, you're working with an ion and you're working with a dipole. So the combination will be an ion dipole.
Okay.
Does that make sense?
Yeah.
Sweet. Okay.
Does anybody else have questions on that stuff or this question? Will the bond between polar negatively charged and polar positively charged amino acid be considered an ionic bond or an ion dipole? So if it's between a negative and positive, that's an ionic bond. That's like the definition of an ionic bond.
Yeah. If they're both charged, if they're both oppositely charged, then yeah, that'll be an ionic bond.
Does this count for the weekly check-in? It's not technically supposed to, but if you like email one of us and say that you were here, then that's fine.
Yeah. Email Jason so he could do it.
That works.
Yeah.
All right. Now we'll talk about tertiary and quaternary.
Am I talking about this?
Yeah.
Okay, so we mentioned the bonds that happen in primary and secondary structure. Just as a quick recap, the only bonds in primary are covalent peptide bonds. The bonds in secondary are only hydrogen bonds, which are non-covalent, and they only occur between the backbone. They do not involve R group interactions. So in tertiary and quaternary structure, now you could work with covalent bonds, you could work with hydrogen bonds, with everything, with either the backbone or the R group. We have a summary about this later, so don't worry about like frantically writing it down now, but I'll elaborate. So like I was saying before, if you're working with a polar charged R group, that will form an ionic bond. So for instance, yeah, the lysine and the aspartic acid, let's say like what someone mentioned earlier, let's say you have an ion, whatever. Let's say you have an amino acid that's an ion. It has a charge, and it interacts with another amino acid that is not charged, but is polar. The resulting interaction is called an electrostatic interaction, but that could be either a hydrogen bond, that could be an ion dipole. So what do you guys think? In the comment section, could you drop down for me, what do you think this interaction would look like? Would it be covalent? Would it be ion dipole? Okay, cool. Cool, yeah. This would technically be an ion dipole because you're working with something that is an ion, right? This charge means that it's an ion. You're working with something that's an ion and something that's polar. So this would be an ion dipole. Now, someone said hydrogen bond, and personally, I personally would agree with you a little more, but okay, I don't want to confuse you, but in like inorganic chemistry, when you talk about bonds and stuff, that's very different from this class. So something that I hope helps is everything that you've known about bonds or electrostatic interactions in other classes, completely just suspend that, because that will not help you in this class. In this class, know that if you have an ion, if you have a charge, and it interacts with an uncharged but polar species, that's technically an ion dipole. For the purpose of this class, that's technically an ion dipole. And an H bond is just two polar uncharged species coming together that obviously are fluorine, oxygen, and nitrogen, and that have a hydrogen. Okay, so polar uncharged groups can make H bonds. Okay, with other R groups. Okay, yeah. So just to elaborate a little bit more what I'm saying, if you have two polar charged R groups coming together, you're gonna get an ionic bond. If you have a polar charged and a polar uncharged, you're gonna get an ion dipole. If you have a polar uncharged and a polar uncharged coming together, the result will probably be a hydrogen bond. And again, these H bonds, the R groups can make hydrogen bonds, but only for tertiary and quaternary structures. Remember, the R groups are not involved with any kinds of bonding in primary or secondary structures. This is solely when we talk about tertiary and quaternary, do R groups start doing dipole, or excuse me, ionic dipole or H bonds. Yeah, okay, and then the last kind of bond is two non-polar R groups coming together. So that's pretty much everything in this table. Whenever you try to interact two non-polar species or amino acids together, the result is going to be a van der Waal interaction or London dispersion, whatever. And that's because they're non-polar, they have no opportunity to bond with each other. They're not attracted to each other. They're pretty much just repelled from each other because they have no charge. They have no charge or partial charge. So the only way for two non-polar R groups to interact is through van der Waal interactions. That is the only way they will interact. So, okay, I was gonna ask a question, but I just answered it here. So yeah, hydrophobic van der Waal interactions will typically be found inside the protein. And the reason for that is because inside the protein, you have all your non-polar R groups. Okay, so any questions about anything I just said about polar, uncharged, polar charged, non-polar? Okay, I'll move on. I'll talk about. Okay, so this is just a summary of, oh, sorry. Is there an interaction between non-polar and polar? Yes, you will get an interaction. What did I call that in?
Isn't that the dipole?
It's, okay, in chem, that's technically it's an induced dipole-dipole interaction. So in like my chemistry class, that would take an interaction between a non-polar and a polar molecule would technically be, it'd be an induced dipole-dipole interaction. For this class, what would we call that? Van der Waal or dipole van der Waal? Because that's important. Like you could definitely see a problem like that.
I thought that was dipole, but
so all dipoles are polar, and if a dipole interacts with a non-polar species, I know what I would call it is an induced dipole-dipole interaction. But for this class,
we can check with Laura and get back to you.
Yeah, just to be like absolutely certain. I don't want to say something and then you put in an exam and you get like that question wrong because of me. So we'll probably get some clarification on that and we'll get back to you about the specifics of that name. But anyway, going back to the bond summary. So again, know the difference between your covalent bonds and your non-covalent bonds. Covalent bonds include peptide disulfide, which we'll talk about in a minute, and Here, remember ionic is always between polar charged, hydrogen bonds is between polar uncharged, and van der Waal is between nonpolar ones. Here, again, in primary structure, these are the bonds that you'll concern yourself with. These are the species that do those kinds of bonds. Same thing with secondary and tertiary quaternary. Okay, so if you could like learn anything, definitely like learn this, because this is these will be primed for like exam material questions.
Okay. Well, pretty much the last thing we're gonna go over is disulfide bonds. So disulfide bonds only occur between two cysteine molecules. That was the only one with, or I think it was the only one with sulfur.
I think there's another one with sulfur, but the sulfur is very tucked away.
Yeah, so it's the only one with sulfur exposed. So yeah, so disulfide bonds occur between two cysteine molecules that they're primarily found in tertiary structure, and they work to pretty much add stability to the molecule, right? So, for example, I'll ask you a question. We'll do this one first. What if the protein, actually, sorry, never mind. So disulfide bonds are covalent, like we said. They're only found, they work to stabilize the tertiary structure, but they also are found in quaternary structure. Laura talked about today that she said that they're rarer in quaternary structure, but they still occur because they're in our group interaction. So basic question, is this single peptide chain in primary, secondary, tertiary, or quaternary structure? We're looking at this one. Yep, someone said it was in a tertiary structure, and that's correct because it's a single polypeptide chain. If you added another polypeptide chain right next to it, then it would be quaternary. Okay, so another question going off this. Suppose a protein needs to bend and flex around very easily to carry out its function. Would you expect to find many or few disulfide bridges? Yep. Lots of people are saying few, and that's correct because like I said, disulfide bonds create stability, and if it needs to bend around, then the disulfide bonds would make it harder to bend around and flex. So you wouldn't find it in a protein that needs to do that. But what about if the protein was an antibody and had to travel around in the bloodstream? Would you find few or a lot of disulfide bonds? Yep, you'd find many because the bloodstream is an aqueous solution and it's full of lots of things that could disrupt the bonds. So you'd want a protein that is as stable as possible, and disulfide bonds would help it do that. So you definitely find disulfide bonds in like the quaternary structure of that protein. And these are just examples of quaternary structures. So the one on the left is an antibody, and one on the right is just a protein with multiple polypeptides. Does anybody have any questions about disulfide bonds or tertiary quaternary structure? Oh, I guess it's not. Sorry, let me reshare one more time. We only have like one thing left. Sorry, this thing's so finicky. Okay. All right. Last question. So this is something that you would definitely see on a quiz or exam, but with different numbers, obviously. If the protein you're working with is 400 amino acids long, if you mutate your protein of interest at the 384th amino acid, have you mutated an amino acid closest to the N terminus or C terminus? Yep. So proteins go from N to C. So C is at the back end of the amino acid, and 384th is much closer to 400 than it is to 1. So you'd find it at the C terminus. There was a question, if you don't have a secondary structure, can you have a tertiary structure? So proteins don't have to have a secondary structure. You could skip that entirely. So yeah, so tertiary structure is just like a polypeptide formed and with the R groups and everything. So yeah, you could definitely have a protein without secondary structure. I don't know of any, but there probably are some that exist. So true or false, solubility in water changes if a protein unfolds. This is definitely like, this is kind of like the thinking questions that Laura would ask on an exam. Yes, it is true. Can anyone explain why though? Either, just probably easier to unmute yourself real quick, but you can type it too. Yep. So you guys got it. So the reason the solubility in water changes is because if a protein unfolds, then the hydrophobic that have been tucked in the inside will come to the outside, and then that will make it harder to dissolve in water. Is there anything else to that?
That's about it.
All right. So that's all we have. Does anybody have questions about what we just talked about, or general course questions?
Domain, subunit, or whatever.
Do you want to try to explain it?
Sure. Okay, so you know your protein has, so that's your protein, and you know that the hydrophilic polar R groups are on the outside, right? Whereas on the inside, you have tucked away all of your hydrophobic ones, the ones that repel itself away from water. If the protein unfolds, now you've exposed both the hydrophobic and the hydrophilic sides. So because the hydrophobic R groups that were originally tucked away in the middle, because they're now exposed into the water environment where water is polar, obviously, it's now not dissolving into the solution as well. So if you've ever tried to mix oil and water, you know that the oil doesn't mix with the water, obviously, it floats on top because oil is hydrophobic. So the same deal goes with the proteins. If you expose the hydrophobic sides, the ones that repel water, it's not going to dissolve in the solution as easily anymore. It's going to, it's called aggregation. It's going to clump together with other hydrophobic R groups and make this bulky, gross thing. Does that answer your question? Cool.
Awesome. Any last questions? Thank you guys for coming. Appreciate it. Just email one of us real quick, or just me, jbendo@umass.edu. I'll send out the slides, but my email's on the first slide too.
And we'll post this to YouTube.
Yeah, I think we'll post the link to this review session somewhere, and you'll see it on Moodle.
Yeah.
Awesome. Have a good night, guys.